everyone, this is Professor Miana. Math2 Day4 lecture. It looks like I've worked out all my kinks, hopefully, and this is going to go smoothly. So we're going to revisit section 1.1 in regard to finishing up discussion on, combining functions. So that'll be operations with functions, difference quotient, which is basically a couple of operations, and a little bit of function composition to boot. And then we'll formally discuss function composition and then wrap things up with word problems, aka modeling functions in section 1.6. Y'all's favorite, I'm sure. Okay, so here we go. To wrap up section 1.1 on functions, let's introduce several function operations. The four basic ones are sum, difference, product, and quotient, and they are defined in ways that I feel like are very probably straightforward, especially if you've ever seen this before. When you want to find the sum of two functions, you simply take the outputs of those functions and sum them up, and find their difference. It's defined accordingly, and so on and so forth. So this chart is just a little bit of an overview of that. And then as far as the domain is concerned for the function operations, you're basically looking for the intersection of the domain of the individual functions, and you have to rope into that with the quotient, just eliminating the value in which the denominator function, in this case generically g of x, is equal to 0. Okay, so there's a particular combination of operations that we'll be focusing on, called the difference quotient. So that's going to be, yes, look at that, difference quotient. I want you to put that in the blinks there. That's going to be something that we are going to introduce here. Later on, it'll become more relevant to you when you talk about differentiation in your Calculus 1 course. For now, let's just go ahead and use it as an opportunity to practice a difference of functions, same functions essentially. It's just in two different places divided by some value h, in which h cannot be equal to 0. Okay, so that's the brief introduction that I have to this material. I think it's most advantageous for us to just start practicing. So here are two functions. F of x is the square root of x, g of x is 3x minus 5. So let's go ahead and find the function sums, difference, product, and quotient in parts A through D along with their domains. And then, of course, we'll find the output values of specific inputs for E, F, G, and H. So starting with A, let's go ahead and add F and G together, which is just take your F of x, the square root of x, and add G of x, which is 3x minus 5. And notice that all three of these terms, none of them are like terms, so we actually can't combine anything at this point, but we can talk about the domain, which is going to be simply x such that x has to be greater than or equal to 0 by virtue of this incorporation of the square root of x there, okay? Now the difference is going to be a little bit more work in that we take our f of x and the square root of x and then we subtract off the quantity 3x minus 5, which is going to require that we do an extra bit of distribution with this sign. I didn't mean for that to be so thick. Let's make that a little bit thinner. Alright, for next time. And then that'll be square root of x minus 3x plus 5. The domain, again, being x just has to be greater than or equal to 0. If we are taking the product, take your square root of x and multiply it by the quantity 3x minus 5. And then we'll distribute. And that'll give you, oh, excuse me, let's keep up with convention here by having it 3 times x times the square root of x. That'll be the order of those elements there. And then minus 5 times the square root of x. Again, the domain is the same. Nothing changes there. X still needs to be greater than or equal to 0 by virtue of having a square root of x inside the function operation. And then here, with the quotient, we have to be a little bit more careful with the domain. But here's what the quotient looks like, just as you would imagine. So there's nothing really we can do as far as simplification is concerned, but please do note that the denominator needs to be restricted in such a way that x cannot take on a value that makes the denominator equal to 0. So that means the domain therefore becomes, hold on, x such that x of course is still greater than or equal to 0 because there's a square root there, but then also x cannot equal 5/3 because that's the value that will make the denominator equal to 0 and make the rational expression undefined. Okay, great. Let's move on to these next exercises down here. And these ones we can kind of use pieces of what we came up with beforehand in order to move the process along more quickly, because we already have what f plus g of x is up here in part A. So then let's go ahead and take that and just every time you see an x, and what we have as our final answer, plug in a 3. So that'll give you the square root of 3 plus 3 times 3 minus 5. So that'll give you square root of 3 stays in the radical. This becomes a 9 minus 5. What's 9 minus 5? That's 4. So you have a final answer of the square root of 3 plus 4. And I'll go ahead and box that up as well, just to make sure that it's clear that that's my final answer. Great. Moving on. What was f minus g of x? Well, that was this guy right here. So go ahead and use, and by this guy I mean the square root of x minus 3x plus 5. So plug in a 4 every time you see an x, and we can go from there. Oh, sorry. No, that's right. Plus 5. Yep. Sure. Yes, that we take the right version of this. Those signs did indeed change. And we will have, well, the square root of 4 is a 2. Minus 12 plus 5. So that'll be negative 10 plus 5, which is negative 5. That's our final answer there. Moving on to part G. Remember, take what's already been given to you here, and every time you see an x, plug in a 2. Minus 5 times square root of 2. 6 root 2's minus 5 root 2's. That's 1 root 2. Or just called root 2, square root 2. If you like that. Not into the whole brevity thing. Okay. Here we go. Let's take this last one. Oops, let me see if I've got more room. Oh yeah, more room at my disposal. Here we go. It's the square root of 1 over 3 times 1 minus 5. That'll give me, the square root of 1 is thankfully just 1. 3 times 1 is 3, minus 5 is negative 2. So go ahead and take that negative sign and plop it in front of the fraction 1/2, and you are done with part H. Okay, great. Moving on. Let's find the difference quotient of f. That is, find f of x plus h minus f of x all over h. Of course, h cannot equal 0, and let's be sure to simplify. Okay, so moving on. Difference quotient. So take this into account here. This is your f of x. So your f of x, excuse me, f of x minus h is what I meant. Let's erase this a little bit. Minus h. Or plus h, rather, sorry. F of x minus f of x all over h. For this particular function, f of x right here, it would be 5 times the quantity, x plus h, all over x plus h minus 4. Now you can have your x plus h in the denominator inside of parentheses at this stage, or you can leave them off. You'll find that in the next step in simplification, you're going to have the parentheses drop anyway in the denominator because there's no reason to have them. But in the numerator, you really need to have them so you can do the the distribution that's appropriate in the next step. So then from that, subtract your f of x exactly as you see it here, which is the 5x over x minus 4. And all of that should be over an h. Great. Now let's go ahead and see how much space did I give myself. Okay, I gave myself that much space. Cool, cool, cool. So notice in your, what I call the supernumerator, that's everything above the h at this point, has subtraction of two rational expressions. So for here, we really need to get a LCD going. The LCD, sorry, that's supposed to be a D there, is x plus h minus 4 times x minus 4. Okay, so you're going to need to create a common denominator here, and it's a lot of work, but I'm going to show you all the steps, okay? So here we go. Next, I'm going to show you a simplified version of this, where I show you what the resulting products will be. Actually, I'm not going to show you every single step, but I'm going to leave it up to you to try this yourself, and if you find that you need or would like more explanation on this, I'm happy to give it. So we're going to have an extra factor of x minus 4 happening in the numerator this first little bit, and then we'll subtract off 5x. We're going to have an extra factor because you want to look for what's missing in their denominators, and that'll determine what factors of the LCD go in the numerator space, x plus h minus 4. And that's all over x plus h minus 4 times x minus 4. And all of this is over an h. Okay, so then we will need to do a lot of multiplication here and here, and then in the next step we'll be able to cancel a bunch of stuff out, and then we'll divide by an h, which I'll do in a very particular way, so hopefully that'll all make sense and feel good. Here we go. Distributing the 5 over the x plus h, x minus 4, I am left with 5x squared minus 20x plus 5hx minus 20h. None of those are alike terms, so let's go ahead and distribute through this subtracted off 5x over this trinomial, so to speak. We have minus 5x squared. See how that's already going to cancel with something up here? Yeah, a lot of stuff's going to cancel. Minus 5hx minus 20x. Or plus 20x, excuse me. Because that negative and that negative distribute through to be plus 20x. And this is all still over x plus h minus 4, x minus 4. And now this is over h. Cool. What a mess. Don't worry, we'll get through this. Alright, go ahead and find all your instances of opposite terms and cancel them out. Here we go. The 5x squared cancels out with the subtracted off 5x squared. Same is true for this subtracted off 20x and 20x there. And then we have 5hx as well. And so notice that I have different slashes for different groups of things that cancel. I think that's very helpful in order to get through this with relative ease, okay? So then you'll notice that you're left with just basically this that you have to deal with. So I'm actually going to go up a little bit and use some empty space in this region over here and show you what's left. So moving on from here, I am left with negative 20h over x plus h minus 4 times x minus 4. And all of that is over an h. So notice that we're dividing by an h here. You can also call it dividing by an h over 1, which I think is useful for thinking about it in like how to deal with dividing by this. So it'll be negative 20h over x plus h minus 4, x minus 4. And then you'll be dividing by h over 1 or multiplying by the reciprocal of 1 over h. And so those h's are about to cancel here and here. And you're left with what is now your final answer. And I'll make sure I box it up in the celestial print here so it'll really pop. Negative 20 all over the quantity x plus h minus 4 times the other quantity of x minus 4. And that's the difference quotient for that particular problem. Okay, a lot of work, and you know what, there are even more details that I could have shown you here, so just let me know if you would like to see some more detail on a particular type of problem or a different one that's similar. Okay? Whew. So that wraps up section 1.1 on operations involving functions and the difference quotient. So let's move on to composite functions. Okay, so in the previous section in 1.1 that we just finished, we talked about when you add, subtract, multiply, or divide functions, how to do it. Now, what if you wanted to feed one function into another function? Well, that's what function composition is. And so what I've done here is I've lifted a couple of figures out of your textbook, and sorry they're a little bit wonky, because the Pearson website was down when I was creating this. I had to scan these with my phone and then upload them into JPEG. So, you know, they look a little bit low rent, but hopefully you get the idea of what is meant by these figures, which is just to say that if you are trying to take an input value into your function that's being composed, g is being composed in f. This is how you would read this right here in this notation. So it's like first you have g and it's being fed into the f function. So it's like you take your input, and you guys are going to like this. I take my x and first I g it, and then I take the output of what happened in the g function and then I f it. You like that? First I take my x and I g my x, and then I f my x. I f it. I don't know. I just get a kick out of that a little bit because it sounds like I'm saying a swear, or I'm trying to say a swear. In any event, so if you're wondering how the domains and the ranges of these things kind of work out, hopefully this visual is going to be a little bit advantageous to everyone's understanding. And these were color-coded. I had to take them in black and white because that was the only way that they were coming out well in this, but in any event, if you want to take the an input value from the domain of g, which is where you're starting from, you always have to start from the innermost function as far as your notation is concerned. Then you have to take your input value and first put it in the innermost function, and then you're going to get an output of g, which is going to be part of the domain of f, is going to be your g of x, right? Because if it's going to be inside of the f function, then that means that the output for g is an input for f. And then you have this going over to the f function, like the f function does something to that output of g, and then you have the value of f of g of x, or sometimes called fog of x. I don't know if that's anything that anybody's ever heard of. You can call it that. Fog of x means that you g is composed inside of f. If it was goth, you know, that little open dot acting as an O as far as the verbal representation of it, then it would be g open dot f. And in that case, you would have your input value go into the f function first, then the output of that go into the g. So it'd be effing it first and then g-ing it. That makes sense. All right, so here's another visual that's associated with this particular series of steps. First, you take your input of x, and then you put it into the g machine, and then the g machine gives an output called g of x, and then you feed that into your f function, and that's how you get your ultimate output of g composed inside of f. It's a lot of different ways to describe this particular notation right here, okay? But as far as the functionality of it, I would stick to what we are seeing right here. That kind of says it all. First, you're going to take your input value of x, whatever it is. If it's unknown to you, just leave it as x. If you have a particular value, you can plug in that value, put it in your g first, and whatever you get out from g, that's what you feed into the f function in order to get the ultimate output here. Okay, let's have a little bit of practice. Here's some exercises. Number 36, multiple parts. We're gonna G and then F it for part A, F and then G it for part B, F it and then F it again, and then G it and G it again. Okay? Cool, cool, cool. And we're not even gonna bother with practicing, I guess, together as a group. We could do some practice as a class later if we want to, time permitting. Or you can ask questions about it if you see it in your homework when you plug in actual values for these function compositions. But let's go ahead and practice. So, you know, we have these two functions. F of x is x squared plus 4. G of x is the square root of x minus 2. So if we have the f of composed in G, that's going to be f with g of x inside of it. Okay, so the way that I like to do it is I like to first, I guess, kind of look at the f of x structure and notice that the input, the x, is being squared, and then I add 4. So basically I want to leave a big empty space inside some brackets and then say, okay, whatever I'm going to feed into my f function, it's going to be g of x in just a second, I'm going to square it and then I'm going to add 4. Now, what actually gets fed into f? Well, not just x, but the entire function of g of x, which is the square root of x minus 2. And that's going to be the initial structure of f of g of x. Okay, now there's some simplification that we need to do, but I think it's good to talk about the domain first before we do our simplification, because there are nuances associated with this initial look of the function composition that lead to the domain. So let me go ahead and off to the side, I'll put D colon, this is how I usually write my domain, and say to myself, okay, what is the domain with of this function composition with its current structure? Well, notice we have a square root, and anytime you have a square root involved in your function, you need to make sure that the radicand is positive or equal to 0. So what values can I take on for that? Well, x has to therefore be greater than or equal to 2, right? Because a 2 would make it 0, and then everything bigger than that would make it positive as far as the radicand's value is concerned. So the domain is that x should be greater than or equal to 2. And then it could otherwise be any other value, okay? So let's go ahead and simplify this a little bit just by recognizing that the square root and the square ring are inverse operations of one another, so they cancel each other out, and we're left with, oops, let me go ahead and switch back to blue. It'll be x minus 2 plus 4, which will be x plus 2 as our final expression, x plus 2. That's our f of g of x. Cool. And I'll go ahead and box that up too, just to make it really finalized. Great, moving on. Now let's go the other direction. Let's first f it and then g it, right? But as far as writing it down is concerned, I would focus on the g of x function and say, well, what am I doing here? It's a square root, and then here is the input. It's x, so whatever I should be plugging in, minus 2, but what was, it's not x that I'm plugging in, it's f of x, which, look back up here, is x squared plus 4. So I will have x squared plus 4 go inside of those brackets. So hopefully that's pretty much understandable. And sorry, I can do this preliminary step, which kind of illustrates what I'm trying to do here. The f function is now being fed into the g function. So I like to look at g first, leave a space in where the input structure is, any x's in the g function, leave a bracketed space open, and then feed inside of it, not x anymore, but whatever the other function is, in this case f of x. Okay, so now I need to recognize that I don't really need these brackets anymore, and I could just combine like terms for the constants, and I will get, oh, and also as far as what is the domain might be a good thing for us to do before I do any simplification. So I'll go off to the side, just say what the domain is. Well, notice that the input value is being squared inside of the radical, so there's no possibility that I can get a negative number being in the working in the real, number set. So any real number is actually going to be good as an input here. So domain is all real. So I'll go ahead and indicate that with that fancy R. Moving back over to the simplification, now I can just call this the square root of x squared plus 2, which is what I'll get when I have positive 4 minus 2. And that cannot be simplified any further. X squared plus 2 is not factorable, so there's really no more that I can do there. So I'll just call it done. Okay? Great. Moving on to f composed inside of itself. So this will be like you have f of x. So take your f function of x squared plus 4, and instead of the first x, go ahead and just say, okay, whatever I'm feeding into my f function, I'm going to square it and then add 4. But what goes in here? X squared plus 4. Okay, so take the shortcut, square this binomial here, and you'll get x to the 4th power plus 8 x squared plus 16. And then, of course, you have to add 4 after the fact. And that'll give you x to the 4th power plus 8x squared plus 20. And, sorry, even looking back on this over here, we have what? Quadratic in nature kind of a function. It's actually a fourth degree polynomial. Anyway, it's definitely going to have a domain of all round numbers. I kind of breezed over that a little bit before I started my simplification, but luckily, I have my work shown, so I could always go back and think about it if I need to. X to the 4th power plus 8x squared plus 20. That'll be it. Now let's g it and then g it again. G of x for this last function composition example. G of x. Fun. So we're going to square root something and then subtract 2 from that, right? Because this is the structure of g of x, g of something, g of, I'm not sure yet, but what's the something that we're going to put inside of here, which replaces the x in the original function? It is the square root of x minus 2. Yep. So you may be looking at this and being like, oh, well, I don't really need this anymore. You are correct. But this stuff is still stuck inside of a square root there. So you may be wondering, well, how do I deal with this in regard to determining the domain? Well, you will want to take this bit right here, the radicand of, the outermost square root, and you want to set this greater than or equal to 0, right? So that'll be the square root of x minus 2 minus 2, okay? The entire radicand of what I would call the main radical. And so go ahead and solve that. You're going to add 2 to both sides, and then that'll get rid of that. You'll have the square root of x minus 2 is greater than or equal to 2. Let's go ahead and square both sides, and you will get, I'm going to just continue over here, x minus 2 is greater than or equal to 4. Add 2 to both sides. Now I'm still talking about domain here. That's the extent of this conversation. X is greater than or equal to 6. Alright, so that's your domain. X such that x is greater than or equal to 6. Get some set notation around that. Call it the domain. But as far as the function composition is concerned, I really just want to keep it with this. So I'll go ahead and rewrite it just for completeness. This is just the square root of the square root of x minus 2 within the main square root, okay? And that is your g of x. Great. Cool, so fun. Let's go ahead and, for this next exercise, look at an already composed function h of x, and let's determine what f and g would be appropriate in order for this function composition to equal this already composed function. So essentially what we're doing is we're like f of g of x is going to equal h of x. So we got to look at the structure of h of x and determine what would be appropriate inner function and what would be appropriate outer function. So from what I can see, it seems to me like the outermost function or operation is going to be this absolute value. So the absolute value of x, I would say, would be f of x. And then the inner bit, the stuff inside the absolute value, it would be appropriate to have that be your g of x. So other similar problems, I would recommend you tackle them in a similar way. Look at the structure of your already composed function, which for exercises that are similar will be called h of x generally, and see if there's an inner function and an outer function that you can identify, and then you'll separate those into g of x and h of x respectively. Okay, so if I'm not mistaken, that wraps up my spiel on function composition. I'm sure you have lots of questions about other problems that have different kinds of structures to them. Let's go ahead and let them rip on the when we have discussion time in class. I have 2 more word problems that I wanted to go over with you, and I have the benefit of experience of seeing from who was it? One of you had a question at the end of class that we didn't get all the way through that was similar to this one, but not quite the same. This one is actually a little bit less complex than the one that was posed as a homework question during the class period, but it has similar elements. Okay, so it's a geometry question. I lifted it straight from your book in section 1.6, and basically for this section, mathematical models, building functions, you really just have to take the hints every time they give you a hint. Try your best to use it, although full disclosure, when I went through this problem, I didn't really use their hint all that much. I went a little bit of a different way with it. I didn't actually find r squared. I found r, and then later I guess I did find r squared, and you kind of have to find it. No, you don't, actually. You don't have to find r squared. You just need to solve for r to find the circumference. Anyway, so what is this problem saying? It's an equilateral triangle is inscribed in a circle of radius r. See the figure, express the circumference c of a circle as a function of the length x as the side of the triangle. So it says first show r squared equals x squared over 3. Okay, so what I did is I said, all right, look, we have a circle, and I'm going to draw a bigger version of this so I can kind of pick it apart. And then we have an inscribed equilateral triangle. Here's the center. I'm just going to redraw it so it's bigger and I can pick it apart. So all of these edges are x, right? So that means that if I was to draw a vertical line here, so sorry about my drawing being not that great, in such a way that it formed a right angle, then I know that this length right here would be half of an x, right? Half an x. Or x over 2 if you like. This length is of course r, and what do I have? I have a 30-degree angle here, a 60-degree angle there. 30, 60, 90 right triangle dictates that the shorter edge of this unknown length, in fact, let me go ahead and erase this x real quick so I can put it here on the outside, and so I could say that this length is what? Well, it should be half of r. Or sorry, yeah, half of r. Or r over 2 if you like, whatever. Okay, but and then the relationship between the shorter leg and the longer leg is that the shorter leg multiplied by the square root of 3, which is this, is supposed to equal the longer leg of, let's just call it x over 2. Alright, So if this is the case, we can solve for r here, which I think would be very advantageous to us. So let's go ahead and cancel the 2's on both sides, and then that'll give us square root of 3r equals x. So then we just need to divide both sides by the square root of 3. And then rationalize the denominator. Ultimately, we will get that r equals x root 3 over 3. Okay, so if you want r squared, you would get x squared over 3, right? Because the root 3 squared would become a 3, and the 3 squared down below would be a 9, then cancel out the x squared over 3. That's all well and good, but what is the circumference formula? Well, circumference equals 2 pi r, so therefore you would have the circumference in terms of x as being 2 times pi times r, which is actually x square root 3 over 3. Now, do we want to rearrange these items in order for it to be upholding convention? Well, sure. So I believe if you're looking up this answer in the back of the book or some such thing, it would be 2 pi square root 3, and x would be all the way at the end, and then you'd have your 3 down below. And that would be your final answer. Just a rearrangement of the elements in order to keep up with conventions. All the numbers should be in the front, and the variable in the back, and then of course, yeah, the denominator. And if you wanted to have your x completely separate, you could have it as 2 pi square root 3 over 3 and multiply that by your x. That would be fine as well. Okay, so maybe a little bit different than what you might have done if you were looking at this from another perspective here. But here's one way to do it. Okay, one last problem, and then we'll be done with lecture. We are filling a conical tank, or what does that look like? A snow cone, kind of a cup, right, or some such thing. Let's say we were pouring water into this device, and we wanted to model the volume changing as a function of the height of the water, okay? And please note the hint that the volume formula for the cone of radius r and height h is given as v equals 1/3 pi r squared h. Cool. So if we want to express the volume v in terms of just the height h, then it's our job to be able to find the relationship between h and the other variable r, okay? So notice that when the cone is completely full, so a full cone has a height of 16, right? And the radius is 4. Now, as the level of the water goes, is like less than that, and it approaches a full cone, the relationship between the height and the radius is proportional. So that means that we can highlight this relationship and have it replace one or the other variable in the volume formula in order to come up with this volume function in terms of just one of the variables, in this case h. So can we rewrite h in terms of r, or vice versa? Well, you might notice that h is 4 times your r if you're taking out the numbers, right, and trying to find the multiplier to get from one to the other. And furthermore, if you wanted to solve this for r, you would divide both sides by 4, and you get, well, r is equal to h over 4. Okay, so go ahead and take this volume formula and plug in h over 4 for r, and then you have the volume in terms of just h as desired. So that initially will look like 1/3 pi, not r squared anymore, but h over 4 squared. And then there's another factor of h. It's really just the simple. This is the trick to it, okay? So do a little bit more simplification. This will become h squared over 16 times another factor of h. Now everything is being multiplied. All of this stuff is in the numerator space, and all of this other stuff is denominator. So let's go ahead and simplify a little bit more. We can have pi and collectively h to the third power in the numerator. Let me go ahead and give myself a little more space here. And then have that all divided by what's 3 times 16? It's 48. And that is your v of h. Great. Okay, so there are more of these problems, different types. Let's go ahead and discuss them as needed in the discussion portion of the lecture. Go ahead and let me know what you've got. Thanks, guys.